Hi, I'm Matt Dragon. Welcome to our classroom for the Private Pilot Virtual Test Prep Lesson number 1. Now, in this lesson, we'll study basic aerodynamics to learn why and how an airplane flies. Aerodynamics deals with the shape of the aircraft, the motion of the air around it, and the forces acting on it. Together, these factors determine the aircraft's ability to fly. We'll begin our lesson with a discussion of the 4 forces of flight: lift, weight, thrust, and drag, followed by aircraft components. Then we'll focus on center of gravity. We'll explore stalls. We'll check out load factor, take a turn at spins, followed by stability. Then we'll look at wake turbulence. We'll learn a little about left turning tendencies, and we'll study ground effect. Right now, let's go to our classroom and join our instructor.
Hi, I'm Josh Pruzik, your instructor for this lesson. We'll begin our session on aerodynamics with the study of the 4 forces. This is the ubiquitous Cessna 172. All airplanes, whether it's a training plane like this or a giant 747, are affected by the 4 forces. The 4 forces act on all airplanes in flight, and the first force is called lift. Lift is opposed by weight, which is the total weight of the aircraft as affected by gravity. The propeller produces thrust to move the airplane forward in the air, and thrust is directly opposed by drag. One way the production of lift may be explained is by Bernoulli's principle. Professor Bernoulli discovered that when the velocity of a fluid increases, the pressure decreases. Looking at this example, you can see that when the liquid passes through the unrestricted tube that you see right here, it flows at a constant velocity. When the tube is restricted, such as this tube down here, the liquid's velocity must increase to travel through the restriction. This reduces the pressure in the restriction. This is Bernoulli's principle, often called the Venturi effect. Let's take this example and apply it to an airplane wing, also called an airfoil. An airfoil is a surface designed to generate lift. The airplane wings and propeller are examples of airfoils. As the wing moves through the air, the airstream is separated by the wing's leading edge, forcing air to flow over the top of the wing and below the bottom of the wing. Notice the shape of the airfoil. The top portion of the airfoil is curved. Notice the air molecules traveling over the top of the wing have a greater distance to travel than those on the bottom surface of the wing. This is called the wing's camber, while the bottom portion is flat. Let's place this into motion. Here, the air molecules are moving up over the top of the wing. Because of this increased distance, the air molecules have to accelerate to catch up to the air molecules on the bottom surface of the wing. According to Bernoulli's principle, this increase in velocity means a decrease in air pressure above the wing's top surface. Under the wing's bottom surface, air molecules do not have to travel as far. Now, these molecules don't accelerate as much, and therefore the air pressure is greater than that over the wing's upper surface. The product of this differential pressure is called lift. This lift production is a function of camber and airspeed. Lift increases exponentially with airspeed. For example, doubling the airspeed increases lift, but not linearly, exponentially. Aeronautical engineers can calculate the lift in pounds per square foot required to get an aircraft airborne. For example, a wing with a length of 30 feet by 7 feet has a wing area of 210 square feet. At 50 knots, for example, a pressure differential of 10 pounds per square foot would easily lift a 2,000-pound airplane airborne. But it's not the only thing that causes lift. Let's take a look at something else. In addition to lift generated by the shape of the wing, there is deflected lift. This is based on Newton's third law of motion. It states that for every action, there is an opposite and equal reaction. Imagine extending your flat hand out the window of a car traveling 80 miles per hour. Wind strikes your hand and pushes it backward and upward. As the air flows under the wing of an airplane, the air molecules are deflected downward by the bottom surface of the wing. This downward deflection causes an upward counterforce, providing additional lift to the wing. Lift is opposed by weight. The weight of an aircraft is the combined load of the airplane itself plus the pilot and passengers, fuel, baggage, etc. Now, weight pulls the airplane downward because of the force of gravity. Weight opposes lift and acts vertically through the center of gravity. We'll discuss this in greater detail in just a few moments. The third of the four forces is called thrust. Thrust is generated by the propeller. The propeller blades are curved airfoils. Now, as these airfoils rotate, a pressure differential is created between the front and back surfaces of the propeller blades. This pressure differential manifests itself as a low pressure on the front propeller blade surface and a high pressure at the back of the propeller blade. This result is thrust, and that pulls the airplane forward. The final force acting on an airplane is drag. Drag is the resistance of an airplane as it experiences motion through the air. Drag opposes thrust. There are two types of drag, induced and parasitic drag. Now, induced drag is the necessary byproduct of lift generated by the wings. Parasitic drag is caused by non-lift producing surfaces such as the struts, the landing gear, the tail, and the fuselage impeding air molecules as the aircraft moves through the air. Both induced and parasitic drag oppose thrust and slow the airplane down. To summarize, these are the four forces affecting every aircraft in flight. Lift is opposed by weight, and thrust is opposed by drag. In straight and level unaccelerated flight, lift equals weight. Thrust also equals drag. The four forces are equal.
Okay, let's take a look at our first question in lesson number 1 regarding the four forces of flight. And that question is, what is the relationship of lift, drag, thrust, and weight when the airplane is in straight and level flight? Now let me give you a little time here to review the possible answers. Okay, the correct answer is A. Lift equals weight and thrust equals drag. Okay, let's get with our instructor now to cover another topic. This one, aircraft components.
The best way to look at these major aircraft components is with a routine pilot procedure called a pre-flight inspection or a walk-around. This procedure is done prior to each and every flight and is a good way to illustrate the components of your typical general aviation airplane. It's important to use the checklists in the airplane's flight manual or pilot operating handbook when conducting this inspection. This systematic approach ensures that you do not miss a thing. Our pilot performs a typical pre-flight inspection of a general aviation single-engine airplane. He'll focus on the main aircraft components using the checklist found in the aircraft flight manual. A typical pre-flight inspection begins in the cockpit with a check of the fuel gauges and other instruments, as you see here, then moves to the outside of the airplane. For our purposes, the pilot starts his inspection by inspecting the propeller. The propeller generates thrust, one of the four forces in flight. Next is the cowling, comparable to the hood of your car. It surrounds the engine and protects it. The cowling and its shape help cool the engine by directing air through and around the engine. Next is the fuselage of the airplane. It encloses the cockpit and the flight deck or pilot position and passenger compartments. The aircraft controls are located by the pilot and co-pilot seats. The fuselage also provides an area for passenger seating and for a luggage compartment. The fuselage starts at the front of the cowling and goes all the way back to the tail of the aircraft. Now, here is the wing of the aircraft. You can see it right here. The wings are airfoils attached to each side of the fuselage and are the main lifting surfaces that support the airplane in flight. The curved shape aids in the production of lift as it moves through the air. The area at which the wing is attached to the fuselage is called the wing root. You can see that right here. The area furthest from the fuselage is called the wing tip, and that would be shown right here. Now, fuel drains are typically also attached on the underside of the wing, allowing you to check for and remove fuel contaminants like water and dirt from the fuel tanks and fuel lines. This is done before each and every flight. This is the pitot tube you can see right here. It senses the impact air pressure, or ram pressure, which is the air striking the airplane as it moves forward. It sends this information to the airspeed indicator displaying the airspeed. The pitot tube will be discussed further in the flight instruments lesson. Now, this is called the stall warning vane or the stall warning horn, and you can see that in this graphic right here. The stall warning horn detects and warns the pilot of an inadvertent stall. A stall causes an airplane wing to stop producing lift. And we'll cover stalls in greater detail a little bit later on. The front of the wing is called the leading edge because it leads the plane into the air. The back of the wing is called the trailing edge. The chord line is an imaginary line that runs from the leading edge to the trailing edge of the wing right through the center of the wing. You can see that right here. That's called the chord line. I'll use this term chord line when discussing concepts like angle of attack a little bit later on in this lesson. The ailerons are attached to the wing's outer trailing edges. They roll or turn the airplane left or right in flight. The ailerons are the control surfaces that affect movement of the airplane around the longitudinal axis. This motion is called rolling. We'll cover the axis of movement shortly. When you want to turn the airplane to the left or to the right, you would rotate the wheel or move the stick in the cockpit. When the right aileron goes up, air is deflected up, and that pushes the right wing down. This turns the airplane to the right. If you want to turn the plane to the left, rotate the control wheel or the stick to the left. This moves the left aileron up and pushes the left wing down. This causes a left bank or a left turn. The flaps are located on the trailing edge of the wing closest to the fuselage, as you see right here. Now, there are different types of flaps, but they all do the same basic job. As the flaps are lowered, the wing's chord line changes, increasing the wing's lifting force. This change in the wing chord line reduces the stall speed. This also causes the airplane to land at a higher angle of attack and increases the airplane's drag. This is what you want when you're landing. Here's the wing and the flaps attached to the tail end of the wing. Here's the chord line running from the leading to the trailing edge of the wing. As you deploy the flaps, the chord line changes. There is greater camber or curvature of the wing, and therefore it's generating more lift. Besides more lift, it is also generating more drag. This does two things. First of all, the drag allows for steeper descents on landing. Also, on takeoff, the greater lift generated by the flaps allows for a shorter takeoff roll at a higher angle of attack. As we continue our walk around the airplane, I'd like to point out the static port that you see located right here. We'll cover this in greater detail in another lesson. The tail end of the airplane is the empennage, a French term for tail feathers. The empennage includes fixed surfaces such as the vertical stabilizer and the horizontal stabilizer. Now, the movable surfaces of the empennage include the rudder and the elevator. The horizontal stabilizer stabilizes the airplane in the pitch axis. We'll cover this in greater detail a little later on. At the rear of the horizontal stabilizer are the elevators you see right here. Elevators are control surfaces affecting movement around the lateral axis. This motion is called pitch and will be discussed in greater detail shortly. Most Cessna and Beech aircraft, like these airplanes, have a separate stabilizer and an elevator attached to it. On some airplanes, like some Pipers, they have a stabilator which combines the stabilizer and the elevator into a one-piece unit. And when the pilot pushes the control wheel forward, the elevator pivots down like you see right here, and the tail is forced up, causing the airplane nose to pitch down. That nose down pitching causes the airplane to descend. Now, just the opposite occurs if you pull back on the control column. The elevator moves up, forcing the tail down, and the airplane climbs. Now, this is the vertical stabilizer that you see right here. It stabilizes the airplane in the yaw axis. We'll cover yaw in greater detail a little later on. The rudder is attached to the vertical stabilizer, and you can see the rudder is shown right here. The rudder is the surface controlling movement around the vertical axis. That motion is called yaw. The rudder is connected to the rudder pedals found in the cockpit by means of cables or push-pull rods. The rudder pedals are operated then by the pilot's feet. During flight, these pedals are used to move the airplane's nose left or right. On the ground, these pedals are used to steer the aircraft while taxiing. To make a coordinated turn to the left, the pilot pushes on the left rudder pedal. This deflects the rudder to the left, like you see right here. This deflection yaws the airplane to the left. If you want to turn to the right, simply press on the right rudder pedal, and the rudder deflects to the right, and the airplane yaws to the right. Now, let's continue on with the landing gear. Most training airplanes have a fixed landing gear. Other airplanes have a retractable landing gear. And some aircraft have a nose wheel, and those aircraft are referred to as a tricycle-geared airplane. When an aircraft has a rear-mounted wheel, it's called a tail wheel, and is often referred to as a tailwheel airplane or a tail dragger or sometimes a conventional geared airplane. Your flight instructor will give you all the details on how to care for your landing gear.
Okay, let's take a look at a question from our studying of aircraft components. The question is, what is the purpose of the rudder on an airplane? Let me give you a little time to take a look at the possible answers. All right, have you got the answer? Well, of course, we know from our studying that the correct answer is A, to control yaw. The purpose of the rudder is to control yaw. Ailerons control overbanking as well as roll. All right, let's get with our instructor once again and study center of gravity.
The center of gravity, or CG, is the point at which an airplane would balance if it were possible to suspend it at that point. It is the theoretical point at which the entire weight of the airplane is assumed to be concentrated. Here's the center of gravity on a Cessna 172 shown here. There are three axes of movement passing through the center of gravity. The longitudinal axis passes through the airplane from front to back. The movement around the longitudinal axis is known as roll and is controlled by the ailerons. This is controlled in the cockpit with the yoke or the control stick. Now, the vertical axis extends from the top to the bottom of the aircraft perpendicular to the longitudinal axis. Movement around the vertical axis is called yaw and is controlled by the rudder. In the cockpit, this is controlled with the rudder pedals. Third is the lateral axis. And you can see the lateral axis right here along the wings. Movement around the lateral axis is called pitch, and it is controlled by the elevator. In the cockpit, it is controlled with the yoke or control stick. The longitudinal axis, as viewed from the front of the aircraft, is illustrated by this aircraft in a left-hand turn. The pilot is controlling motion about this axis with the ailerons. Notice how the airplane rotates around the center of gravity. The lateral axis is illustrated from the side of the aircraft, shown here, as the aircraft pitches up and down about the center of gravity. The pilot is controlling this motion with the elevator from the cockpit. The vertical axis is depicted here as the aircraft yaws about the center of gravity, first to the right and then to the left. The pilot is controlling this motion in the cockpit with the rudder pedals.
Okay, let's consider a question now in our study of the three axes of movement. And that question is, pitch is movement in which axes? Give you a little time to study the possible answers. Okay, we of course know that the correct answer is A. Pitch is movement in the lateral axes, nose up or nose down. Okay, let's continue with our instructor now for a new topic. This one, stalls. And of course, in consideration of stalls, the airfoil.
Now is a good time to discuss chord line and how it relates to the angle of attack. We'll begin by studying stalls. A stall occurs when the wing's critical angle of attack is exceeded to the point at which the wing does not produce lift. To understand this, we need to define the angle of attack. Here is a typical cross-section of a wing. The leading edge of the wing and the trailing edge of the wing are shown right here. Now, here's the chord line, that imaginary line that passes right through the center of the wing from the leading edge to the trailing edge of the wing. Remember, camber means curvature, and you can see the camber right here. The upper and lower cambers are shown in this graphic. The mean camber, then, is the line drawn between the upper and lower surfaces of the cross-section of an airfoil. The downwash angle shown here is the angle at which the air flowing over the top surface of the wing departs the trailing edge. The relative wind is the airflow direction with respect to the wing's attitude. Now, the relative wind is parallel and opposite to the direction of the flight path of the aircraft. The angle between the chord line and the relative wind is called the angle of attack. The angle of attack is important for other concepts of aerodynamics. The angle of incidence is the angle at which a wing is attached to the aircraft's fuselage. The pilot has no control over the angle of incidence. It's actually established by the aircraft designer.
Okay, let's consider a question now regarding the angle of attack. Our question is, angle of attack is defined as the angle between the chord line of an airfoil and the... Give you a little time here to consider the possible answers. Okay, you have your answer? Of course, we know it's A. The direction of the relative wind defines the angle of attack. All right, let's rejoin our instructor.
Here is a wing in level flight. Air is moving over and under the wing in a nice, smooth flow. This is called laminar flow. But notice as the angle of attack is increased, there's a little bit of burbling going on right back here at the trailing edge. The critical angle of attack is the point at which airflow over the wing separates from the wing surface. This creates turbulent airflow. This turbulent airflow no longer produces lift. If you continue to pull on the control column, the angle of attack increases and the wing eventually enters a stall. The air moving over the lower surface is undisturbed, but check what's happening right here on this wing's upper surface. Airflow has separated from the wing. Lift is no longer generated because the critical angle of attack has been exceeded. A stalled wing is not producing any lift. To recover from this, reduce the angle of attack and it will begin to produce lift again. Stalls occur at the same critical angle of attack regardless of altitude. In order to understand why, you have to first understand a little bit about air density. Air density closer to the ground means the molecules are tightly packed. But as we climb in altitude, notice that the molecules are less dense or less tightly packed. Let's take a look at how this affects our aircraft by looking at these instruments in the cockpit. The indicated airspeed will be the same at higher altitudes than at sea level. Therefore, true airspeed will be higher. You will not be able to tell from your indicated airspeed that the aircraft is stalling at a higher true airspeed. Let's take a look at another example in this graphic shown here. This aircraft is flying at a high density altitude. At high density altitudes, the wing stalls at a higher true airspeed because there are fewer air molecules. And this makes sense because with fewer air molecules, you need to fly at a greater angle of attack to generate the same amount of lift that you would generate at a lower altitude. Therefore, the wing will reach the critical angle of attack at a higher airspeed. Now let's take a look at one last graphic to illustrate one other important concept. This aircraft shown here is in a descending flight path, and we can see that right here. Notice the relative wind coming up from below. The concept we're showing is that a given wing will always stall at a given angle of attack. You can see right here that even though the aircraft is descending, the angle of attack relative to the relative wind is great and has actually been exceeded. And therefore, the aircraft is in a stall. The critical angle of attack can be reached in any flight attitude at any airspeed.
We are very pleased today to have Mr. Bruce Williams with us in the studio. Now, Bruce is a veteran pilot of over 30 years. He's also an active flight instructor specializing in technically advanced aircraft, simulation instruction, and stall, spin, and upset recovery training, as well as aerobatics. Bruce, welcome to the studio.
Great to be here.
Now, you mentioned that you specialize in stall, spin, and upset recovery training. How does that type training differ from what a pilot would normally experience?
Well, every pilot has to do a certain amount of stall training, regardless of the type of certificate or rating they're working on. But they do what I call sort of textbook stalls, and they perform a series of almost scripted maneuvers for the tests that they take. And those of us who provide stall, spin, upset training try to take things a little bit further and give people a little bit more experience, because I found over the years that there are an awful lot of pilots who are nervous or uncomfortable with stalls and spins, stalls especially, and even some instructors are a little bit uncomfortable with that. So we just try to get people in an appropriate airplane with an experienced instructor in conditions where we can really explore stalls and spins and upsets in more depth than they can in a typical training scenario.
Can spin type training be accomplished in pretty much any aircraft?
Well, there's a bit of a misconception out there. A lot of people think that any airplane that the FAA has certified has been spin tested, and that's just not true. A normal category airplane, which is most of the airplanes we use for our training, has only been tested to what's called a departure. It's basically a one-turn rotation after a stall. And so once you get beyond that point, it's not entirely clear what's going to happen next in an airplane unless it's been spin tested. So it's really a good idea if you want to go beyond what I call those sort of textbook stalls to get into an airplane, an aerobatic airplane that has been approved for spinning. And it's really important also to remember that most people think that an aerobatic airplane and the spins in particular, it's all about the stresses, the G loads and so forth. And what it really is about is controllability. What's going to happen to that airplane after it gets into a developed spin, and does it have the rudder authority, the elevator authority, and other control effectiveness in order to get out of the spin? And that's why you need an aerobatic airplane.
Now, I understand the FAA doesn't really require a pilot to have spin training, but they have to have what is called spin awareness.
That's right.
How does a pilot become aware of spins without some training, some formal
That's
training?
right. Well, the rules say that only flight instructors, when they're getting ready to take their flight instructor test, have to demonstrate competency in actual spins. But every pilot, if you're getting an airplane category rating, so that's airplanes, gliders, and so forth, has to have stall spin awareness training, which is mostly ground training. And the examiners are supposed to test you on that. So obviously you read the books and you discuss the phenomenon with your instructors, and presumably you do a series of stalls in an airplane and see what those are like. But that's about as far as it goes.
To summarize, the critical angle of attack can be reached at any airspeed, be it in straight and level flight or a 60-degree bank. You can reach that critical angle of attack at any airspeed at any attitude. The flight attitude is the attitude of the airplane in relation to the horizon. It can be in a climb, nose-down attitude, or even straight and level flight. The airspeed at which a stall occurs is determined by the weight, load, and the altitude.
Okay, continuing our examination of angle of attack, we have another question for you. That question is, the angle of attack at which an airplane wing stalls will, give you some time here to study these answers. Well now, do you have it? Let us help you. The angle of attack at which an airplane wing stalls will, C, remain the same regardless of gross weight. A little further explanation here. A stall is a rapid decrease in lift caused by the separation of airflow from the wing's surface, brought on by exceeding the critical angle of attack. The indicated airspeed at which a stall occurs will be determined by weight and load factor, but the stall always occurs at the same angle of attack. Very good. Now let's move on with our instructor to a new topic, load factor.
When an airplane is banked into a turn, a portion of the vertical lift being developed is diverted into a horizontal lift component. It is this sideward component that forces the airplane from straight and level flight and causes it to turn. The reduced vertical lift components result in a loss of altitude unless total lift is increased by increasing angle of attack, increasing airspeed, or both. This load is the force that must be supported by an airplane's structure in flight. The loads imposed on the wings in flight are stated in terms of load factor. In straight and level flight, the airplane wings support a load equal to the sum of the airplane plus its contents. This load factor is equal to 1g, where g refers to the pull of gravity. However, centrifugal force is generated, which acts toward the outside of the curve anytime an airplane is flying a curved path, such as turns, climbs, or descents. Whenever the airplane is flying in a curved flight path with a positive load, the wings must support the weight equal to the weight of the airplane plus the load imposed by the centrifugal force. In short, turns increase the load factor on an airplane. An increased load factor will cause an airplane to stall at a higher airspeed. Some conditions that could increase the load are overloading the airplane, too steep an angle of bank, turbulence, and abrupt movements of the controls. Notice our airplane is in a coordinated turn. To produce this coordinated turn, you need to use the yaw and the roll axis of the airplane. That is, the rudder and the ailerons must work together. As the airplane moves into a turn right here, there's an increased load on these wings. We can measure all this. The vertical component of lift lifts the airplane in this direction. The horizontal component that you can see right here increases as the airplane moves into the turn. As the load increases on the airplane wing in a coordinated turn, you have to increase the amount of lift being generated by the wings. This is because part of the vertical component of lift is being diverted into a horizontal component, resulting in a loss of altitude. The shifted lift force is due to this resultant lift. Load factor of a wing is the ratio between the resultant lift and the airplane's weight. We can use this graph that you see right here. It's called a load factor chart, and it's typically found in your aircraft's operating manual. Now, down here on the x-axis are some bank angles in degrees. These are angles of bank we may use during our flight. On the vertical axis right here, you can see the load factor. Let's say that on our flight, we're going to fly with a 45-degree bank angle as shown right here. To find the load factor, we would follow the bank angle up to the intersection of the curve and read 1.5 times the normal load factor. That means our wings now have to generate 1.5 times more lift in flight. To compute this, we take our airplane's weight, which in this case is 4,500 pounds. You know this because you've completed your pre-flight preparations. This preparation includes a weight and balance calculation. You know your passenger's weight, your fuel weight, and other items packed into your airplane. We simply multiply that weight by 1.5 times. This tells us that our wings now have to generate 6,750 pounds of lift to compensate for our turn to keep us in a level flight in a coordinated turn. Here's another instance. Let's look at this chart right here. We can see that we are flying with a 60-degree bank angle. Following this up to the intersection of the curve, we can read that our bank angle has resulted in a load factor that is now twice the normal load factor. So in our example, we will need exactly twice the amount of lift to generate what we would in level flight.
All right, let's take a look at a question covering load factor. That question is, during an approach to a stall, an increased load factor will cause the airplane to... Give you some time to look at the possible answers. Okay, do you have your answer? Let's share. During an approach to a stall, an increased load factor will cause the airplane to A, stall at a higher airspeed. Okay, stall speed increases in proportion to the square root of the load factor. Thus, with a load factor of 4, an aircraft will stall at a speed which is double the normal stall speed. Make sense? Okay, let's continue with our discussion on a new topic, spins. Back to your instructor.
All right, let's talk about spins. A spin occurs when both wings stall, and in some cases, one wing stalling before the other. An aircraft will spin only after it is stalled and will continue to spin as long as the outside wing continues to provide more lift than the inside wing and the aircraft remains stalled. As an airplane's wing increases past the critical angle of attack, the wings will stall. Lift will not be generated. However, if an airplane begins to roll or yaw towards a wing that is in a greater stalled condition, one wing has stalled before the other. This starts a rotation or a turn in the direction of the stalled wing. A spin has now been entered.
Well, you have to remember, a spin happens only when there's a stall and a yawing moment. So to get into a spin, you have to have all of the signs of a stall that you would probably be accustomed to, such as the sound of the air flowing over the airplane changes because you're going slower. The controls get a little bit sloppy. They don't respond as crisply as they did at normal cruising speed. All those normal signs you've learned about as being part of a stall happen before a spin. But the big difference is, usually because the airplane is in a yaw, the stall is much more abrupt, happens much faster, and you'll typically feel a wing drop, either the left or the right. And so you'll feel what feels like a roll. It's really a consequence of the yaw. But the airplane suddenly, the wing drops, the nose pitches down, and it's a much faster, more aggressive type feeling or reaction of the airplane than you would in a normal training stall.
Okay.
As the spin becomes fully developed, its path resembles a spiral turn as the plane rapidly descends. Now you can stop a spin by reducing the angle of attack. This in turn allows the wings to start producing lift again.
Well, I think, again, you have to distinguish between an incipient spin, that departure that I just talked about, and a fully developed spin. It's kind of hard to get into an unintentional fully developed spin. So most of the stall spin accidents you hear about are these departures, these incipient spins. And as long as you haven't gone more than about one full rotation, again, just breaking that stall, reducing the power so you're not driving towards the ground, breaking that stall, getting the airplane flying again will really help. You get control of the airplane and you can climb away then. If you're in a fully developed spin, however, things are a little bit different. The airplane has had a chance to stabilize, it's rotating, it's coming down at a very steep angle. Airspeed is very slow. So what you want to do is make sure that the classic recovery technique, which works well in almost any airplane, power to idle. Adding power doesn't help things at this point. Ailerons neutral. You don't want to be sort of fighting the airplane or trying to get out of what you think is a roll by applying opposite ailerons. So just neutralize the ailerons. Then apply full rudder against the direction of rotation. So if you're rotating to the left, spinning to the left, you push that right rudder all the way to the floor and hold it there until the rotation starts to slow down. And then as the rotation slows down and stops, then stick forward to break the stall and get the wing flying again.
Well, you may have just covered a little of that, but how does proper recovery from a stall prevent a spin?
Right. Well, obviously, as I just said, you can't spin if you're not stalled. So if the spin hasn't had time to develop, if you've just had what we call a departure, wings drop, the nose is pitched down abruptly, the first thing you want to do is stop doing what you were doing. Relax that back pressure. You're probably pulling back on the yoke or the stick. And if you just relax that back pressure or push forward a little bit, you'll break the stall, and that rolling moment will reduce or go away, and the airplane will start flying again. So if you've just departed, and that wing has dropped abruptly, don't try to pick it back up with a bunch of aileron, to roll the wings level. Just relax that back pressure, get the wing flying, and then you can recover before the spin has a chance to develop.
Very good. Now I want to check this question. What are some of the aerodynamic factors related to spins, and how might pilots evaluate the aircraft they're flying for a likelihood of a spin occurring?
Well, let me start first with the fact that a lot of folks are confused about the stages of a spin. And a spin doesn't happen instantly. An airplane can't go from normal flight to a fully developed spin in a finger snap. It takes a little while. It has mass, it has momentum, and aerodynamic forces take a while to develop. I like to say it takes a little while for nature to solve all the equations of motion, just doing the math. But obviously, aerodynamic factors, the airplane has a great deal to do with it. How big is the rudder? How big are the ailerons? Is the elevator blanked out under certain conditions? And so you have to put all of those into effect. And obviously an airplane, the weight and balance of the airplane can affect it. And so that's why you have these different categories of airplanes that the FAA certifies: normal, utility, and acrobatic, at least in our small airplane world. And that's largely based on how they're going to react under these conditions. So the aerodynamic factors are really complicated. You're into what the engineers call nonlinear phenomena and so forth. But you're basically stalling the wing, and then you have a yawing moment. The airplane's rotating around that vertical axis, and when those two factors combine, that's when a spin can start to happen.
Very good. Now, what are some of the flight situations that are most conducive to an unintentional spin?
Well, the classic example that everybody cites is what we call the base to final turn. So you're coming into land at an airport, and you're on what's the base leg. You're 90 degrees to the runway, and maybe you go a little bit past it, you overshoot. And so you try to compensate for that, but you don't want to make a steep turn in the traffic pattern. So you try to help it around a little bit with some rudder. Yeah, so you push a little rudder. Let's say we're doing this classic left turn, and so you push a little too much left rudder. Well, that makes the nose drop as well. So then you try to bring the nose up by pulling back, and you keep doing this, and this cycle sort of feeds back on itself, and then at some point you have this rapid departure. It's a stall, just like all the others, but everything happens much faster than you're used to in your training stalls. And that wing drops, the nose pitches down, and you start to rotate. And of course, you're low to the ground at that point, so that's not a good situation. That's right.
Not good.
Now, there are some other situations that are sort of similar. For example, let's say you do a go-round. For some reason, you've decided you don't want to land, and so you apply full power, but you don't add enough right rudder. So the airplane starts to yaw. You try to compensate for that by holding in a little aileron, and then the nose pitches up because you had it all trimmed, for landing, and now you've added all that power, and the trees are getting bigger, so you pull up a little bit more, and you're in basically the same situation, except now you have full power in. And again, you're yawing, and as soon as the airplane stalls, you're going to have that abrupt departure. So those are sort of two classic examples where that can happen. There are other situations where perhaps you're maneuvering, and you're a little too aggressive with your maneuvering. You do an accelerated stall, and the airplane's yawing. There's a variety of situations, but those are sort of the basic ones that we encounter in the accident statistics anyway.
Now, since spins is such an important topic, we thought we'd take time to test your knowledge with a question. The question is, to stop a spin, a pilot should, 3 possible answers. We'll give you a few seconds here to study them. Of course, you know this answer. To stop a spin, a pilot should C, reduce power, apply rudder opposite the spin direction, and release back pressure. Now remember, to stop a spin, you must get the wings flying again. Thus, stop the rotation first by applying opposite rudder, then release back pressure to break the stall, and reduce power to keep the aircraft from exceeding the normal airspeed. That all makes sense, I'm certain. Okay, moving on with our instructor to a new topic. This one, stability. See you in a few.
Did you know that airplanes are inherently stable? That means they want to fly. Stability is the tendency of the airplane to resist movement away from its flight path. In other words, it's the tendency of the airplane to seek the same direction of motion in which it was prior to being disturbed from its original flight path. A well-designed airplane is both maneuverable and stable. The more stable an airplane, the less maneuverable it's going to be. For example, a Pitts Special is going to be much more maneuverable than a Boeing 747. The more maneuverable an airplane, the less stable it is. An airplane which is inherently stable will require less effort to control. A stable airplane quickly returns to its original attitude, and this is called positive static stability. A neutrally stable airplane normally stays in a bank turn or will eventually return to level flight. It has no inclination to make a bank steeper or shallower until you, the pilot, make the control input. If the airplane is not stable, you can get into some real problems with the center of gravity and aircraft loading. The center of gravity has a natural tendency to pull down on the wing. You can see that right here. Behind the center of gravity is the center of lift, or COL, and its natural tendency is to push up on the wing. But there's still this natural tendency for a pitch down occurrence. So how do you counteract that? You do that with balancing forces. These balancing forces are generated by the propeller. As the air moves along the fuselage over the wing, it strikes the tail in such a manner that it impacts the top portion of the tail. That is negative lift, and it is also called a tail down force, and it counteracts that natural pitch down tendency. Now assume you're flying in straight and level attitude. You pull back on the yoke and release the yoke. The natural tendency of the airplane is to oscillate until the center of lift and that tail down force are equal. This returns the airplane to stable flight. If you reduce power, thus reducing airspeed, the airplane's nose now pitches down. This is because low airspeed reduces the amount of downwash on the elevators from the prop slipstream. In turn, this reduces elevator effectiveness. Let's take a look at an example of how all this works. Here are 3 examples of a longitudinal stability and how an airplane stays within its center of gravity envelope. Here is the center of gravity shown right here. Here is the center of lift, and notice how the center of lift is located behind the center of gravity. Now notice how much tail down force we have. Also note how effective the elevators are. This airplane is properly loaded with fuel, passengers, and baggage. In the next example, notice the center of gravity as we see right here on the graphic. Now let's take a look where the center of lift is this time. The center of lift is actually behind the center of gravity, but much closer. Let's take a look at the tail down force. We still have tail down force present, but notice that it's much less than before. Also notice the elevators are less effective. Maybe you have luggage out of place, perhaps you have too many suitcases in the back, or perhaps your heaviest passenger should really be sitting in the front seat. Finally, let's take a look at this third example and see what happens when the center of lift is located ahead of the center of gravity. When the animation starts, note the location of center of lift in relation to the center of gravity. Notice what happens when there is no tail down force and insufficient elevator control to properly control the aircraft. Here you can see the center of gravity, and the center of lift is located ahead. There is an actual pitch up force, which creates an extremely dangerous condition. One of the greatest challenges you will face as a pilot is making sure your aircraft is loaded within its center of gravity envelope. If you get the weight too far back, you may not be able to recover from a stall because you do not have enough elevator authority. This is a very dangerous situation. The center of gravity limitations will be discussed in detail in the lesson on aircraft performance.
Welcome back, and in our examination of stability, let's take a question. The question is, what determines the longitudinal stability of an airplane? Now, there are 3 possible answers. Let's take a moment to have a look at them. Okay, do you have your answer? All right, let's look. What determines the longitudinal stability of an airplane? Of course, the answer is A, the location of the CG with respect to the center of lift. Okay, let's move on to another topic. This is wake turbulence. And back to your instructor.
Wingtip vortices are a byproduct of lift. Typically, larger airplanes, such as this one here, generate a lot of wingtip vortices. They are most noticeable when an airplane is heavy, slow, low, and clean. In other words, the flaps are retracted, and so is the landing gear. Here's how they're generated. As we discussed earlier, when the wing generates lift, there is lower pressure on the wing's upper surface and higher pressure on the wing's lower surface. Out towards the wingtips, that pressure rolls off the wings. It rotates up into the wing's upper surface. Now the higher pressure is rotating to fill that void of low pressure. Wingtip vortices then roll off counterclockwise off the back end of the wing. Typically, they move away from the airplane laterally at a speed of about 4 or 5 knots in a no-wind condition, and usually they fall off, descend below the wing area at a rate of about 400 to 500 feet per minute. Here's what can happen if you get into a situation where there's some wind and perhaps a parallel runway like we see right here. Here we have runway 9 left, and over here is runway 9 right. Look what happens when you have a quartering tailwind and a large aircraft landing on 9 left. Remember, wingtip vortices are most noticeable when the aircraft is low and slow, like you'll have in a landing configuration. With this quartering tailwind that we have right here, check what happens. These wingtip vortices travel from 9 left right across onto 9 right. And if you're landing on this runway down here in a small airplane, this can potentially be a very hazardous condition. How do you avoid wingtip vortices? Let's take a look at this graphic of a large aircraft landing here and talk about some concepts that will help you avoid dangerous situations. Notice as the large aircraft comes down for a landing, it creates a wingtip vortice up until the point of touchdown. If you're flying in a smaller aircraft, you want to note where that aircraft touches down and make your touchdown point beyond his point of intended touchdown. Now, let's take a look at another concept that involves takeoff. Watch as the large aircraft takes off from this runway. The wingtip vortices begin at the point of rotation and climb out. If you're flying in a smaller aircraft, you want to note where that larger aircraft takes off and make your point of rotation in front of that larger aircraft's point of rotation, and your intended climb path should be before the climb path of the larger aircraft. This will allow you to avoid the wingtip vortices of larger airplanes.
Say, we're back and we've got another question for you, this on wake turbulence. The question is, when landing behind a large aircraft, the pilot should avoid wake turbulence by staying. There are 3 possible answers again, fairly involved, so take some time to look them over. Well, do you have your answer? We certainly hope you got the right one. Question again, when landing behind a large aircraft, the pilot should avoid wake turbulence by A, staying above the large aircraft's final approach path and landing beyond the large aircraft's touchdown point. Don't forget, to avoid wake turbulence caused by wingtip vortices, stay above the large aircraft's final approach path and land beyond the aircraft's touchdown point. On to another topic and back to our instructor. This topic, left turning tendencies. See you back here in just a while.
The first of the left turning tendencies is P factor, sometimes called propeller factor. Here's an example of an aircraft in straight and level flight. You can see that right here. And also note this aircraft down here in a climbing attitude. Now take a look at the exaggerated propeller that we see in both of these examples. Remember, the propeller is nothing more than a moving or spinning wing. Now, here's the relative wind over here for both our aircraft in flight. The relative wind forms an angle of attack between the ascending and descending propeller blades. In straight and level flight, the amount of thrust being generated by the ascending and descending blades is equal. Remember, as you sit in the cockpit, the propeller turns in a clockwise rotation, so the descending blade is on the right-hand side. Now, what happens is that when the airplane climbs, the angle of attack of the blades change. The descending blade on the right-hand side of the aircraft will generate more thrust than the ascending blade on the left-hand side of the aircraft, and that has a tendency to yaw the aircraft to the left. Remember Sir Isaac Newton and his third law of motion? It states that for every action there's an equal and opposite reaction, and that helps us understand our next force we'll take a look at, called torque. In this case, the action is the propeller turning to the right, which generates an equal reaction, which is going to be the roll of the aircraft to the left. Now, these forces counteract each other, and the reactive force is called torque. The last left-turning tendency we'll discuss is called spiraling slipstream. Now, as the propeller turns, it generates air moving down the side of the fuselage and over the wings, and you can see that it creates a slipstream. As this air strikes right here on the side of the fuselage and the side of the vertical stabilizer, it has a tendency to yaw the aircraft to the left. Now, the good news is that manufacturers can generally design this yaw out of the aircraft by simply designing the vertical stabilizer in such a way to minimize this effect. Now, there is one other left-turning tendency that is often discussed, and it's gyroscopic precession. Gyroscopic precession is the result of a deflective force being applied to a rotating body like a propeller. Gyroscopic precession says that the resultant action occurs 90 degrees later in the direction of rotation. This is not to be confused with P-factor.
We're back once again, this time with a question regarding left-turning tendencies. The question: the left-turning tendency of an airplane caused by the P-factor is the result of the... You have three possible answers. Let's take just a bit of time to look at them. Getting a little more complex here, but we certainly hope you got it right. Question again: the left-turning tendency of an airplane caused by the P-factor is the result of the B, propeller blade descending on the right, producing more thrust than the ascending blade on the left. Again, tough topic, but we hope you got it right. Moving on to a brand new topic, and our final topic, by the way, ground effect. We will join your instructor now.
When an airplane operates less than one wingspan above the runway's surface, that surface interferes with the airflow being generated by the wing, reducing the wingtip vortices. As a result, this actually improves the aircraft's aerodynamic performance. This improvement is primarily caused by a reduction in induced drag. As a result, any excess speed in landing causes the airplane to float down the runway. This means if you come in for a landing and you're carrying too much speed on final, as you get close to the runway, that is less than one wingspan above the runway's surface, your induced drag decreases. Your wing's performance or lifting capability increases, and the airplane has a tendency to float down past your landing spot. Now, that's not a good thing to have happening when you're trying to land on a short runway. The opposite is true on takeoff. On takeoff, ground effect can cause an airplane to become airborne before reaching its recommended takeoff speed. You get the airplane off the ground, but as soon as you climb out of ground effect, you lose lift.
Say welcome back. This is our final question for lesson number 1 regarding ground effect. The question is, ground effect is most likely to result in which problem? Again, your consideration of these 3 possible answers. Wow. Have your answer? Okay, I'll pose the question again. Ground effect is most likely to result in which problem? The answer, B, becoming airborne before reaching recommended takeoff speed. Remember, Becoming airborne before reaching recommended takeoff speed is something to be careful of with ground effect. Now, when you're ready, please continue with lesson number 2, aircraft systems, and I'll see you a little later.